Okay, so I guess I'll use Desmos for this video. So I'm on my computer as opposed to my pad, or not an iPad, but a notebook anyway. Let's see. So, yeah, that's me down here in the corner. Sorry about that, but so what we'd like to do, I will add a note. So here I'm going to add an item. And if I add a note, it's just a way to make my writing look better. I'd like to compare Euclidean distance with taxi cab, or grid, but taxi cab distance. So there, I put a note in. And to do this, I'm going to make a couple points, and then just, I'm not going to use the distance function in here. I'll just write the two things. But so I need 2 points, and so I'll just have a point A. I'm going to use an uppercase A equals, and it doesn't really matter what the points are here to begin with. Say 1, 2, and there's the point. Now, notice it says label. I can, if I turn on label, then see it says 1, 2 there, but it also has a space here. If I just say A in there, then over here it makes the label A. Now notice, you're having possibly somewhat of a hard time seeing this, and there are various things I could do. I can zoom in a bit. Now I'm just using my mouse wheel to do that, and I could also click here on the zoom in or zoom out, and I think home just takes me to the default look. But the other thing I can do, and you can do this if you're trying to take pictures and so forth to make things look better, I can go here to the wrench, and there are various things. Now, the display, it doesn't really say, it used to say here like presentation mode or something, but it just has these 2 A's. But if I click that, it'll make things a little bigger and a little brighter, and so that's a nice way to go. Now, other things you can do in here is that when you zoom in and out, that both axes zoom in and out. If you want to change one axis, you can come in here after clicking the wrench, and you can actually change what X goes between. So for instance here, if I just came in here and said, oh, make that a 0, see it changes over, and now 0's over here against the edge. But I'm going to go back to the -10 for now, and leave it like it was, and then to get out of there, I can just click. Now also notice this thing is taking up a fair amount of space on the screen, but not a huge amount. I can go over this and kind of move it in and out to sort of change how much room I have in there. So if I decide to do that, I can do that, and I can always click my mouse and drag and move things around. So I've got my 1 point. Now I'll do another point B equals, I don't know, let's go with 3, 4. Okay, because it really doesn't matter at this point. Now I'm going to put my label in here and type B, and so now I can see points A and B. Alright, so what I want to do is just kind of keep track of the 2 distances between the points. So I'm going to start with the Euclidean distance. So I'm going to call that D, And now I'm going to do an underscore key here, and that sends me down. Another thing I could do, if I backspace, I get back up here. If I do a down arrow, oops, no, I was wrong. Okay, well, I can be wrong. So I do an underscore key, and then I'm going to put an E here for Euclidean, and then a right arrow up and equals. And again, that's square root. Now I can get a square root by typing S, Q, R, and notice when I hit T, it turns it into a square root sign. And so I can get it by typing. Now I could also come down here and get a square root sign and all that, but I tend to do my stuff by typing. So I need a parenthesis, and I need AX minus BX. Okay, but I don't want to use the 1 and the 2. I'm going to make this a formula, so I'm going to type A dot X and then minus B dot X. So that's a nice thing about using names and naming things like this is I can get at the X value of my point by just putting dot X, and similarly, oops, I need to square it. So I'd hit a caret, which is over the 6, the arrow over the 6, 2, and then I come back down by hitting a right arrow, and then plus A dot Y minus B dot Y. So this is a very convenient way to get this. And now if I want to see everything, I can always grab this and pull it wider. So now I can see everything in there. And there's my Euclidean distance, and similarly I can do a D, and I'll use the underscore key and a T and a right arrow to get out of there, equals, and absolute value, I just use this vertical line here that's over the enter key above it. And I do that same thing, A dot X minus B dot X. Now you can do some copy and paste. So for instance, if I highlight that, now the thing is, to copy, I can't use the mouse. I have to use Control C. So I hold down the Control key and hit C. And then I can come in here and I can do Control V, and I get that, and then plus, and I'll hit my absolute values again and go up here and Control C and Control V, and there's my distance, taxi cab distance of 4. Now notice that the taxi cab distance is bigger than the Euclidean distance. And now the reason I made these points is, for instance, I can grab hold of B here and I can move it. I can just move it anywhere I want to. And notice, okay, it changes the distances, but the taxi cab distance is still bigger. Come down here, taxi cab distance is still bigger. Can I make it exactly the same? Well, yeah, if I'm real careful and I get this point right on, I need a 1. So if you look, there we go. Okay, I got B to be a 1 and a negative 134. Now notice both of them are the same distance. So if my 2 points are along the grid, to get to each other, if you go straight along the grid without making any turns, then the Euclidean distance and the taxi cab distance are the same. But as soon as I'm off over here somewhere, then the taxi cab distance is bigger, right? And I can move A anywhere I want here. Okay, so I can move either A or B, and every time I do, the taxi cab distance is at least as big as the Euclidean distance, or the straight line distance. But again, that kind of makes sense that if I'm going from A straight to B, that should be shorter than if I go straight up this way and straight over that way. All right, so that straight line distance is the smaller distance. The Euclidean distance is smaller than the taxi cab distance. Although they can be equal, if I come up here and what's B, 1.3, well, we'll try to, we'll get a height of 3, or I'll try to anyway. Now I can always, to move my points, I can always go up here and make that a 3, make that a 3. I could get rid of the decimal place as well, but notice again they're now right along the same height, and it doesn't have to be 3 exactly, so I could do 3.4 and 3.4, and you see the Euclidean height and the Euclidean distance and the taxi cab distance are the same. So that's one comparison of Euclidean distance and taxi cab distance, is that we see then, and I'm going to, I'll probably get an error on this or something, but I'm going to write d sub e, so the Euclidean distance is always less than or equal to the taxi cab distance. And so that I just put as what we found here. It's always, it could be equal, so it is in this case. But again, if I don't have those things along the grid lines somehow, the taxi cab distance is bigger. Okay, now so one more comparison. Let's look at a circle. So I'm going to highlight this whole thing and copy it. So again, to copy, I do a Control-C. Sorry, you can't see me hit those keys. And a Control-V to paste. And that's a little long, so I'm going to make this just a little wider. Okay, so what I want to do is look at all points. I'm gonna set it up a little bit differently here. I'm going to say is equal to, and I'm going to pick a radius, but I'm not going to tell you what it is yet, so I'm going to just do an R. And this is giving me all kinds of errors right now because it doesn't know what I mean. I'm going to say R equals 2, say. So that's a radius of 2. Okay, that's a distance of 2. Now what I want to do is from a single point find all other points that are a distance of 2. So here I'm going to, well, I'm going to use B as my single point. And let's go up here, just, I'm going to make B 0, 0. Okay, so you see it put B here at the origin. And now, instead of using AX and AY, I'm going to use any X value. X and any Y value. And notice what it does is it makes a circle of radius 2. So I made radius 2 here. It makes a circle of radius 2 around B. So this algebraic statement here said, I want all points X and Y such that if I put them in the distance formula here, from this point up here, 0, 0, I get this value 2. And that's a circle. And that is what a circle is It's all points that are equal distant in the Euclidean distance from a given point, and you make a circle like that. Now, though, you could do the same thing with a taxi cab distance instead. You could say, well, I want all the points that are a radius of 2 or a distance of 2 from 0, 0 in the taxi cab metric. Well, so I set up the same thing. So I'm going to highlight that part, do a Control C to do a copy. I'm going to come down here and put it right below here, do Control V to paste, and then say equals R again. And again, I'm going to do the same thing. I'm going to change the AX to just a general X and the AY to a general Y. And what you see is all points that would be a distance of 2 if I were doing a taxi cab. And so let's, I'm going to zoom in a little bit so we can see this a little better. And look, certainly if I start here and I want to go to this point up here, I can go 1 over and 1 up, and that's a distance of 2 in the taxi cab. But if I go straight over, that's a distance of 2. If I go straight up, that's a distance of 2. And so you see that we end up getting what looks like a square, right? But we would call it a circle if we were talking about taxi cab distance. And so if I'm looking at like a city map and somebody says, well, okay, I want to look at everything that is a distance of 2 miles or maybe 200 yards or 2 something from the city center. Here's, say, the city center. Well, you see all of a sudden it matters whether you mean Euclidean distance, a Euclidean distance of 2 miles, because that would include everything in that circle. But if I think of it as going there by traffic, so I need to drive there in 2 hours, then maybe that's, everything's the same speed limit and so forth, and so no matter how I drive, it would take about the same amount of time. Okay, might be true, not usually, but you never know. So I want to look at everything that is 2 miles by city streets. And in that case, all of a sudden, I get what's in the square. And so, if you want to start talking about accessibility, so this is getting back to our overarching problem, and you say, well, we want everybody within 2 miles. Okay, say this is our crisis center or something, and we want to look at everybody within 2 miles. Well, you see, it's not that simple. What do you mean by 2 miles? Do you mean this 2 miles, in which case a person here would actually have to drive more than 2 miles to get to the crisis center? Whereas, do you mean a taxi cab distance, in which case everybody in this square drives 2 miles or less? Okay, so if all these people in the circle could fly straight there, yeah, they're within 2 miles. But if they have to drive, then all of a sudden you've counted them as being in 2 miles, but they're not. And so math is hard, right? It's not that hard to calculate these two distances. Okay, I either use the absolute value stuff to get the taxi cab square here, or I use the square and the square root to get the circle. But it matters which one I use, and I need to understand the difference. And what you see is that the taxi cab distance is always going to make a smaller area. Okay, so a taxi cab circle, whoops, see, I forgot to do note here, so I'm going to put in a note so it types better. A taxi cab circle is always smaller than a Euclidean circle. Okay, so it matters, right? Because if you want to say everybody in this big circle has the same accessibility or no worse accessibility, in other words, they all, and you say it's like all within 2 miles, well, you're wrong. Your math is wrong, because in context, they are not within 2 miles. In context, right, they would have to go along city streets, so they would be over 2 miles away. All right, this person would have to go this distance and then go 2 miles. So they are over this person's over 2 miles away. And, the person might go this way and that way. But again, it doesn't matter as long as you stay on the grid which way I go. And so I can see that it's more than 2 miles. And so you disenfranchise people if you're not careful about your mathematics. And, saying that, oh yeah, these people out here are no worse off than these people here. Well, but they are, okay, because it does take them more than 2 miles to get here. And so that's a difference. A taxi cab circle is always going to be smaller than a Euclidean circle, but it is going to match up at these 4 points, right? So we're always, if we orient our grid sort of north, south, east, west, as you might call it here, then these 4 points, the eastmost, northmost, westmost, southernmost, those points will all match up with the circle. But every other point that's also that same distance is going to be inside, well inside that circle, so it's going to be smaller. Okay, because the taxi cab distance is always at least as big as the Euclidean distance. So that's why if I'm out here, the Euclidean distance is 2 miles, but the taxi cab distance is bigger. And so that I think will serve as our comparison. So again, as we look back, as we compare these, one thing we found was this, that the Euclidean distance is always less than or equal to the taxi cab distance. And then a taxi cab circle is always smaller than, these are really related to each other, these two statements, but a taxi cab circle is always smaller than a Euclidean circle. And again, in context, when you start talking about equity and accessibility and those kinds of things, then those two definitions matter. And actually, just off the cuff here, let's take cases where somebody in the criminal justice system has been sentenced to live outside of a certain distance from, say, a school or some other facility. And so suppose this is your facility. Well, notice, say it's a 200-foot range, and that's 100 feet, that's 200 feet. Then notice, depending on how you talk about distance, you get a different answer as to where that person can live. And so if you mean taxi cab distance of 200 feet from here, then they've got all this place they could live. But if you say Euclidean distance, then they can't. And it makes a difference. It certainly makes a difference to the person who's trying to find a place to live, and it makes a difference to the people who are worried about where that person is living. And so you have to be careful about that sort of thing. I haven't done it yet, but by the time you see this, maybe I'll have found the article. But there is a nice court case that I may be able to find that involves a river. And again, we start talking about definition of distance, and a river causing you to not use either of these distances, not the taxi cab distance nor the Euclidean distance, but a path distance. Okay, a river could cause you to need a path distance, and actually there is a court case that was looked at where a person was exactly doing what I'm talking about here, trying to live in a particular place, and that person's argument was that the Euclidean distance, yes, was the person was trying to look at an apartment or a house within the Euclidean distance, but within the path distance, because of the river that they had to cross, they were not within the whatever it was, 500 feet or 200 feet or something like that. So this definition of distance absolutely matters to people. And so here are some of the mathematics of it, at least with Euclidean and taxicab. And we'll talk a little bit more about the path distance and time kind of ideas. Okay, so we'll call this video done.